I wanted to show today the references. So I mentioned in the passing in the lecture yesterday, right? So one of the very good books you can read, which was published this year, is Computer Vision Algorithms and Applications. So you can do some registration and download the version for free from this website. Okay, so there is this dive into deep learning. We will use part of this book later on when we cover some topics. So it's a very good book with code available, and it has been used by a lot of universities. So it is quite a practical book, which could be very useful when you learn multiple topics. Like, it not only covers computer vision, it has NLP, recommender systems, all those things. So all those different areas also. And this is the book I would be using for today's lecture mostly. Okay, this is a latest book, Deep Learning: A Visual Approach. So it has very nice diagrams through which you can easily understand the architecture. Okay, so we are mostly going to focus on the architecture and how the different networks are built and what is the significance of each of the component in the network. So that's what you are going to see. And in this, there is an accompanying website where you can get the code and figures. Okay, some of the figures I have adapted from this book in my slides, so we will use it directly. So all the figures in the book are free, and the codes, the notebooks are free. So you can all the examples given in the book, you can run through it. So it's also a very updated book which covers all the recent developments in this field. So we want to go till what is the current research area which is happening in the area of computer vision in terms of deep learning. So that's why we are going to use these latest resources. But I don't know, like, we have roughly around 3 hours time. So we'll try our best to capture the overall overall frameworks and the basics required for you to go further after you complete the summer school. So let's go to our notebook. So we stopped here, right? The deep learning algorithm. So someone asks you to define what is the deep learning, right? What's a deep learning? So in one sentence, if someone asks you to define, so there are many definitions. So what I would say is use of neural networks for learning representations. So you have given some data, you want to learn the representations and do some task, right? How to use the power of neural networks to do this task, right? So that is the deep learning. And these neural networks are actually inspired from the physical neurons, but there is not much synergy between the two. So the deep learning people try to make the networks independent of how the physical neurons are, and they do, and go ahead. So let me tell you that we are going to focus mainly on, in the first session at least, we are going to mainly focus on supervised learning. Okay. We are going to learn about the framework called supervised learning. You might have already heard about this supervised learning in the previous sessions, but as an overview, I want to tell. So how to realize the supervised learning if you consider this deep learning or this neural network as a black box, is something like this. So suppose you have a deep network, so it contains a lot of weights. That what is the weight and all we are going to see. So this is the network, and there is this input and there is output. So the network is the same for both the training and the inference or the testing phase, but how you are going to change the weights or use this network is going to determine. Okay. So what we are going to do is the network. So there is a forward pass which you will do. So what you will do is given an input with the label already given, because it's a supervised learning framework. What you will do is you will send the input through the network. So consider only one input. So send the input through the network and then see whether you are getting the desired label or output you want. So we'll consider the classification problem. Okay. So if you don't get, there should be a loss function or a cost function, which needs to be used to go back and change all the weights sitting inside. right? So one forward pass followed by one backward pass, that there is a specific term for that, that is called an epoch. Okay? You keep doing it. So you pass new inputs, then change the network weights, and then keep doing it until the pass function or the error function reaches very low value. Okay, this is the training phase. And there are 3 phases in a supervised learning framework. You might have already learned when you were doing a machine learning session, right? So there is a validation phase. So what you do is you are given a set of any data set, you split it into training set, validation set, and test set. The validation set is used to tweak the network parameters, more fine-tune the network parameters to see how it performs for unseen data, right? So there are something called hyperparameters which can be tuned, right, in the network when through the validation set. Okay, so after the validation set is also passed through the network, the training of the network is complete. So all the parameters are frozen and it is ready for deployment or inference phase or testing phase. So all of them are different terminologies used, right? Pre-trained network. So that's what the term normally used. The pre-trained network is one which has been trained using the training set, and the parameters are adjusted using validation set, and finally you will send the give it to the real data, right? So when the real data comes, then how the performance is, that should be good because it has been fine-tuned using unseen data also during the validation phase. Okay, so this is the supervised learning. So the training phase, you go back and forth, and we are not going to discuss this. The forward pass we are going to discuss. The backward pass, the adjustment of weights is done using an algorithm called backpropagation algorithm. And there are some optimizers which are used to aid the neural network to decrease this error function much faster, or converge much faster, or the minima it reaches faster, so that you can get the training done in a much faster time. So that is the idea. So any doubts with this? So this framework is clear with you. So with this understanding, we will move forward. Okay. So this is an example of a physical neuron where there are a lot of inputs which are received in the dendrites, and this cell body or this soma which integrates all these inputs and then decides whether to fire an action potential through this axon or not. This is the action potential which is going to reach the dendrites of other neurons following. So again, the other neuron will receive this action potential in some form and then integrate it and decide whether to fire an action potential or not. Action potential is a binary phenomena. If the summed potential is below certain threshold, action potential will not be fired. If it is above a threshold, there is an action potential which will be fired. Okay. So that threshold is analogous to a non-linearity we are going to see in the design of the deep learning. And the summing aspect is the integrator or the summing module, which we are going to see. Okay, this is the similarity between them. But the human neuron and the nervous system is very complicated. There are millions of neurons which interact in a highly complex way. So you cannot like draw parallels, and there is not something like a layer and other things we are going to discuss. They are connected in different ways. Okay. So this is the understanding. So now let's go to the history of neural networks, right? So how many of you are familiar with Perceptron, multi-layer Perceptron? How many? Multi-layer Perceptron? Only few of you. Okay. So we'll cover that. Okay. So the actual neural network started with something called multi-layer Perceptron, or the Perceptron itself. Okay. So the simple thing is you integrate a lot of inputs and then pass it through a non-linearity and then feed it to the next thing and so on. So that is the initial thought process of this neural network, which was actually in the 1960s actually. So okay, so there is a 1969 was a very famous book which was published, and after that in the 1970s to mid 1980, so this problem with these neural networks were they were like data hungry, as well as they were also requiring a lot of computational resources. So there was not much development in terms of computers that time. Okay. So this is called the winter of neural networks. So where people were not very much buying the philosophy of neural networks. So that time in the parallelly in the computer vision, the research was mostly based on geometry and the photometry, radiometry, which I discussed in the last lecture, right? So then what happened in 1986, Hinton and colleagues proposed the use of MLP and introduced this back propagation algorithm for faster training and so on. Okay. So then many people did not buy it till then. So 1986 to 2010, so Hinton, Lee Kun and others who got that prize Turing award, right? So they were sticking to still this neural networks. So there was a group which was saying like do the traditional machine learning, extract features and then feed it through a learning algorithm. But these people were sticking to that requires more complicated training process and everything. So you don't go into that. You can do end-to-end thing, but still that computational resources were very less, and they had to stick to that MNIST kind of smaller data sets for their inference and demonstration and everything, but they were sticking to it. But in the 2000s, there was evolution of GPUs and parallel computing, which was useful to process simultaneously multiple neurons and then train them, right? So this and some people used the earlier LeNet, which was the original neural network proposed by them, and then there was a ImageNet challenge, which was won by a neural network in 2012. So that was after 2012, people started believing that neural networks were indeed powerful and they could be used for inference tasks. Still, people were not convinced till 2014, when GANs were released, that neural networks are powerful generators also, right? Inference tasks are recognition tasks and other things, right? The vision tasks. And the generative tasks are what we saw yesterday as a image processing task or computer graphics task, where you synthesize some new imagery or video and so on, right? So after this GANs came about, and then people realized that we can use these neural networks to also generate samples. So there was a boom of GAN, and there is a GAN Zoo also became famous. So all the named GANs were cataloged and people started working on that. Okay, so let's go, because many of you are not yet familiar with this perceptron. Let's go here to understand what is this perceptron, right? So what is a perceptron? So suppose let's take a image is a very million pixel data. So to analyze that on paper would be difficult. So we'll take a simple example where the input is only a 4-dimensional vector. So this 4-dimensional vector, suppose you want to process through a perceptron, the idea is to weigh each of the entry in the sequence, input sequence, by a different weight. Weight 1, weight 2, weight 3, weight 4, and so on. Okay. So these weights we can group into a vector W bar, and this input is the X bar which is being fed. Okay. This W bar transpose X bar is the inner product between that. The entire module could be simplified as W bar transpose X bar, an inner product between the weight vector and the input vector. Okay. So like we also did a approximation yesterday, approximation means the different representation for convolution. So we told that convolution is repeatedly doing a shift and an inner product. Right? Similarly, we are going to see that the neural network or this multi-layer perceptron is going to do repeatedly inner product of the weight vector and the input. That we will introduce. Okay. So then this is similar to this. If you see that real neuron we discussed, so there is a cell body which sums up all the inputs gathered by the dendrites, and then there is a threshold which decides action potential should be fired or not. So that threshold is this. Okay. If it is less than 0, it is -1. If it is greater than 0, then 1. This is similar to this action potential firing. So this is the similarity I was talking about, right? So now there is a modification to it. So sometimes it may so happen that there is a for a this is a affine kind of representation. So you need a bias term. Okay, that was a linear kind of thing. So here you want to have it like an affine thing. So you need a bias term for effective functioning. I will talk about more about the significance of this bias term, right? So the bias term is like a DC component. So it just rises up or level. That so it doesn't change the variations, but it just takes it like it's like an exposure in a camera, you can say, right? So you have a same scene, you take two images, with one with less exposure time, one with more exposure time. So the scene and the content is not going to change, right? The more exposure time image will be more bright, right? That's the analogy you can draw to understand this bias term. Okay? So then this is a bias B, and then the equation will become W bar transpose X bar plus B, and followed by an activation function. Okay. Now this activation function, there is a representation like this also that we will see. So this function is called an activation function. So it was a rule written like this, greater than 0, 1 and else -1. So that is written as a function here, which is also called an activation function. Okay. So every layer of a multi-layer perceptron does this one, or every neuron of the multi-layer perceptron does this one. So it receives input from the input or the previous layer neurons, and then sums them up, adds bias, and then passes through a threshold. And this threshold, there is a special name which is called an activation function. Okay. So we need to understand these components, then we are clear. So now the people told that, so there is a, this looks like this is not a linear equation. So to include the linearity, so always you give one weight to the, so by bias, you make it 1, and this weight for the bias term, you make it this B. Okay. So what will happen is these are the weights corresponding to the other inputs. So bias doesn't have any input. So we send 1 as the input to the bias term. Okay. So then what will happen is this W bar, which is the weight vector comprising of only weights, gets augmented with B. So you will get W dash bar, which is the weight vector. And then this X dash bar is obtained by stacking the input vector along with concatenating it with this 1, which is the input to the bias term. So this is what you will see in all neural networks books. Okay. So the perceptron is nothing. So it is like every neuron does the same task of summing things, adding a bias. So the adding a bias is not a like new feature. Now you will always send 1 also as input, and the bias term is implicit. Bias term also becomes part of the weight vector. That's what I told. So I will tell you one example actually. So for an example, if you so when we discuss autoencoder for an example, so this bias term plays a crucial role in learning some representations. And also some of the times that exposure kind of thing, even in images. So suppose you want to synthesize an image with different exposure, the content needs to be the same, but the exposure needs to be different, right? So that is like a bias, right? It's a DC component, right? So you have a, so someone has a sinusoid, right? Sinusoid with a DC component of 0, or you want to rise it. So all the sinusoid should be above the positive the quadrant. So you want to rise it. So we'll add a bias term. So that role this bias term is playing. Okay. So internally, like if what if the bias term had not been there? So if you have only this weight vector and this input vector, right? So that means it will not be able to capture some variations which are just a DC shift for the entire input actually, right? So that thing, how much it should be shifted, that is governed by this bias term. Okay, so we need to put everything inside that so that the neural network learns by itself. So this variation, you should not engineer something new. So that's why we have the bias term. Okay, is this clear? Okay, so let's move on. So now let's go to a compact representation, which you normally see that the input is given here, and this one and this one. So this is a single neuron of your multi-layer perceptron or multi-layer perceptron. There is no multi-layer still. There is a one layer in that one neuron. What is the representation? That's what we have seen. Okay. Let's move on now. So a neural network may comprise of this kind of complex things. Okay. So, but let's go and understand it using a simple example. So we'll skip some of the things. So this will give you an understanding. So what a multi-layer perceptron is. Okay. So this is an example of a perceptron, or it is also called MLP. So, and some people call this multi-layer perceptron if you want to. So there's some new deep learning expert you ask to define multi-layer perceptron with a single sentence. So they will say multi-layer perceptron is a neural network which has all layers which are fully connected. So you can define multi-layer perceptron after you learn every deep learning that it has fully connected. That means every neuron in a later layer receives input from all the neurons from the previous layer. And every entry of your input goes as input to every neuron in the first layer. So now there is some terminology, we will define it. So these inputs are 4, again we are taking, and the layer 1, which is like not seen by this. So this input itself is called the input layer. So the inputs, we arrange it as a vector, that is the input layer. And the first one whose weights are not visible to us, these neurons are not visible to us. So this is called a hidden layer, right? And next one is also a hidden layer. And the next one is the layer 3, which is the output layer, from where we are going to draw the outputs. Now let's come to the dimensionalities. Okay. Now what we can do is all the weights, right? So this has this first neuron has 4 weights, right? Second neuron has 4 weights, right? The fourth one could be the bias, so that we are not explicitly stating it. So this could be 1 as the input. Okay, so this input is 1, and all the things are bias terms going to different things, so that we are not explicitly giving. So the input, actual input could be 3, but 1 bias is added. Okay, so that we are taking it inside only. So now the third one has also 4 weights. But what is happening? All these set of 4 weights, there are 3 sets of 4 weights. Everyone agree? The layer 1 or the hidden layer 1 has 3 sets of 4 weights, but each of them is multiplying the same input vector, right? So then we can write them as something like this. So the weight vector, this for the first layer, weight vector for the second layer, weight vector for the third layer, all multiply the same input x dash bar. No, we are considering only this. We are now trying to understand only this. So we can stack all the weights as I wrote down, right, corresponding to this as the first row of a matrix, all the weights corresponding to this as the second row of matrix, and all the weights corresponding to this as the third row of matrix. That matrix could multiply the input, and what you get are the outputs of these 3 neurons. Okay. Then I can write the matrix as a W1 matrix because it corresponds to layer 1. It is a 3 cross 4 matrix. 3 rows, each of them has 4 columns. And then each of them will multiply an input of size 4 cross 1. So it will give out a vector of size 3 cross 1, which are the outputs of these 3 neurons. Always the dimension of the weight matrix is going to be the number of neurons in this thing times the number of inputs. Okay, everyone understood this? So next, let's go and analyze the next layer. Now you have three neurons, three inputs are there. Each of them is going to each of the neuron because it's a fully connected layer or the multi-layer perceptron. So how this will work? So this one will have a matrix W2 will characterize this. So what would be the dimension of this? Anyone? What would be the dimension of this W2 matrix? I've already written down 2 cross 3. Because I have 2 outputs I want, but 3 inputs I am receiving each of the neuron, or 3 neurons are in the previous layer. So then it is 2 cross 3. So this guy will multiply all the inputs coming out of the first layer and then produce a 2 cross 1 vector, which would be the output of these 2 neurons in the second layer. Everyone understood this representation? Yeah. So that is implicitly we have assuming that bias term is inside that. Okay. So the next one, this one, the next layer we will go. So here there are 2 inputs. So each of the neuron is receiving 2 inputs and the output is 3. So you will have a 3 cross 2 as the weight matrix, which will fully get all the weights in this. So, and you can easily, so 3 cross 2 is 3 into 2 is 6. So there are 6, this thing, right? 6 connections to it. So similarly, 3 into 2 is 6. So here there are 6 connections here. And in the first one, 12, there are 12 connections here. Fine. So you keep stacking it and finally the output layer. So, and there are how to initialize these weights, right? So this also you want to train, you will just do a forward pass, do a back propagation, change all these weights, and then again do a forward pass. Forward pass is nothing but a matrix vector multiplication. So each layer does a matrix vector multiplication in a multi-layer perceptron. Everyone got this? Okay. So now the how to initialize this, there are many schemes. There is Leaken, Glorat, and Hay scheme, and Glorat and Hay, I think. There are 2-3 schemes. So you initialize these weight matrices, right? Using uniform by samples from uniform distribution or Gaussian distribution, right? Or some probability distribution you initialize. So everything has some different benefits that you can see. And finally, once you initialize, after that, this last function you will define here will take over, because that back propagation is just a partial derivative of that, using which you are going to change the weights of all these weight matrices. Everyone understood this full process? Okay, this is a normal neural network. So let's move on and try to see it as another thing, another way to look at it. Here we had avoided this activation function. Okay, so let's see these neural networks along with the activation function. Suppose after the first layer, I am applying activation function F1. After second layer, I am applying another activation function F2. And after third layer, I am applying another activation function F3. So after the first layer, we will have a vector obtained as an inner product between the rows of this W1 matrix and the input vector X1, right? So this is the thing you will get as output, right? And then this is fed, this vector you get is again multiplied with the rows of this W2 matrix in layer 2. And again, another activation function F2 will be applied. And then it is multiplied by W3, and then another activation function F3 is obtained. So what is the significance of this activation function? So we understood why the bias term is required. What is the significance of this activation function? Anyone? What if activation functions are not there? Not really. So then what is the problem? The function would stay linear, that is correct. And every multi-layer perceptron can be collapsed to a single layer perceptron. Because if that all these things are not there, for an example, this one is not there, this one is not there, this one is not there, you can multiply these matrices W2 times W3 times W2 times W1, you will get a single matrix. that will multiply the input vector. Then you can collapse this multiple layers into a single layer. That is not useful. And the complex interaction between the other one is also correct. In the complex interaction between the input and the output cannot be captured because it will stay linear. Everyone understood this? That is the significance of this activation function. So that's why the activation functions are always non-linear. Okay. So another way to understand this. So let's have another understanding. So this Jan LeCun also states in most of his talks. So another way to understand this is like you can all these weights, right, associated with these layers, you can assume it someone with a sound mixer, right? So someone playing that radio jockey kind of. So you want a very nice, pleasing sound out. So the instruments and different instruments can be controlled with the bass, treble, and many other things. All are knobs actually. So the role of him is to adjust those knobs so that the final output sound is pleasing to the audience. Right. Similarly, the backpropagation algorithm, what the role it plays in adjusting the weights is that the error should be minimum so that the predictions are accurate. So the backpropagation, you can assume it to adjust these knobs, different weights sitting in the different weight matrices. Okay, so every time it adjusts, it sees whether the output error is going down, whether I'm doing fine. If it's not fine, again it goes and adjusts, tunes the knobs, again sees whether it's going down. Right? It keeps doing it until things are fine. So this is a good analogy to understand this. So any questions? So we have completed the understanding of this multi-layer perceptron. But there are some challenges. So that's why we are going to relate what we saw about convolution to this thing. So before that, some of the concepts which are common to these convolutional neural networks and MLP or any neural network can better be understood right away itself, having MLP as this thing. Okay, some more components like what are the choices? Some of the questions which are left open are what are the choices for these activation functions, right? Another thing so all the other things are explicit. There is nothing hidden in there. Another thing is if I want to use this MLP for a classification problem, right? How to massage this output or how to manipulate this output so that irrespective of the range of input, the range of values returned by these different neurons, I am always able to make the correct decision, correct learning for a classification problem. So what is that thing I have to? So what should be the last layer in my MLP always if I am using it as a classifier? Yeah. So that we will see. So many of them are not this thing, right? So this is a very complicated representation, right? So this is very complicated representation. So what we are going to do is this one fully connected layer of a multiplayer perceptron, we are going to represent like this. If it is a cross thing, that indicates that it is fully connected, and 3 indicates the number of neurons in that layer. This is a shorthand representation we are going to use. So multi-layer perceptron, you can, to summarize, it is a fully connected network and it takes raw data as input and makes this thing, makes a prediction. So some activation function examples we'll see. So it's a linear activation function, these, and these, right? Why these linear activation functions are useful? So this has not much use, but this and this, why it is useful? But linear activation function, we saw that if you have linear activation function, the matrices collapse. But why do you need this linear activation? Sometimes they are used. What could be the role of them? Suppose, yeah. So to kind of, this one is a positive thing, but it doesn't serve the purpose. This is scaling the output of a previous layer, right? So if I apply this kind of linear activation before feeding it to a nonlinear activation. So nonlinear activation, you want to feed certain range of values only, right? Suppose you want to scale down the values of the output coming from the neurons of a particular layer. Then you use a linear activation function to just stretch or shrink the values and then feed it to a nonlinear activation function. So this serves that purpose. Okay. So, but some of the nonlinear activation functions, let's see. So one of the activation function you can use is this thing. This is the input axis always. This is the output axis. So, so you clamp it. So all the inputs positive, you clamp it to a maximum value. All the inputs which are negative, you clamp it to a negative minimum value. Okay, this is one of the activation functions, and this is the special cases are this unit step or this Heaviside step. So the unit step, you specify the threshold. In Heaviside step, 0 is always the threshold. So positives are clamped to 0 and negatives are clamped to positives are clamped to 1 and negatives are clamped to 0. Okay. So the operation of this is similar to your clamper circuit. In digital circuit, you use a diode as to design a clamper circuit, right? So something similar. And this unit step is another variant of that. So where all the positive values are clamped to 1 and all the negative values are clamped to -1, right? And 0, what happens? There is ambiguity here. Here, this dot says that 0, you make it 0. Here, the 0 is pushed to 1. There are two variations. 0 you consider as positive here. 0 here you don't consider as either positive or negative. You make it 0 itself. The input itself is 0. Okay. And the most common activation function is this rectified linear unit. So what it does is it passes the input as it is, if it is positive, and if it is negative, it clamps to 0. Right? This is the input, and this is the output. So if the inputs are negative, then their output is always 0. Okay. So you can write this in a simple form as y equal to max of 0, x. So the rectified linear unit never will output a negative value. It's also similar to a half-wave rectifier in a diode circuit if you want to find a similarity. The earlier one was clamper in diode circuit. This is a half-wave rectifier. So the problem with this is it's slow learning rate, because a lot of outputs of the previous layer, you are making it 0. If the output of the neuron is negative, that means you are not taking into consideration the output of some of the neurons. So you will get a lot of dead neurons. Its neurons are physically there in the network, but they are not useful. Right? To change that, the most commonly used one is a leaky value. So you don't make it 0 if the input is negative, but you make it a slight negative value. The positive one, you pass it as it is, but you are scaling down the negative value to something. So this you scale down to eta of x, where eta is very, very less than 1, but close to 0. It's a very small positive constant. But if x is negative only, we are using it. So it will make it less negative. It will make it less negative and close to 0. So this leads to some faster learning rate compared to the ReLU activation. And you can see the choice of this eta, 0.1 or 0.3 or 0.7. You can see that 0.1 clamps down the negative values too much, and you are not like it's as the eta goes close towards 0, it approaches the ReLU activation function. And if the eta is going close towards 1, it is going towards the linear activation function. Eta term decides whether it goes towards ReLU or the linear activation function. And there is another variant of this, which is the shifted ReLU. So what you do is you have a threshold. So if the x is greater than threshold, that means it could take a value of minus a, it is clamped to a negative value. If it is greater than the threshold, you output x itself. So that means you are allowing some small negative values of input as it is. But if it is a large negative value, you are clamping it to some minus. Everyone understood? It's a variant of ReLU. It's called shifted ReLU. And there is something called max out, which is also some people use. So what you are doing is you are trying to build a non-linear activation function using several linear activation functions. Right? In the first thing, if you see it clearly, there is, I think, let's take this example. So this one is a linear activation function. This is another linear activation. This is another linear activation. 3 linear activation functions are there. So always you choose the maximum out of it. At any given point, you go to all the linear activation, whichever is the maximum, that value you keep. So you get the activation function shape as this. Yes. And this is another max out you formed using, I think, 5, right? 1, 2, 3, 4, and 5 linear activation functions. So at every place, whichever linear activation function gives a maximum value, you choose that. So the non-linearity is this. The final non-linearity you will achieve out of this 5 linear activation function is this. Okay. Sometimes you use this as a activation function also. It's max out. So it outputs the maximum response of all the linear activation function for a given value of it. Everyone understood? Okay. These are several choices. And there is a smooth ReLU, whose equation is something like this. So there is a ReLU, there is a discontinuity here. So you make it smooth using ln of 1 plus e power x. And there is smooth shifted ReLU also. So we saw shifted ReLU was like this, but smooth shifted ReLU doesn't have any discontinuity there. And there is a swish function, which is something like this. And this logistic function, which is also quite famous, which is also called a sigmoid function, whose equation is 1 by 1 plus e power minus x, and the curve is something like this. Okay, this sigmoid function was quite famous before the ReLU and leaky ReLU took over. Now most of the people use parametric or leaky ReLU because of easy differentiability and less computation. And tan h is another activation function which looks similar to sigmoid, but the range of the tan h outputs is going to be from -1 to +1. But sigmoid always will output a positive quantity. That's the difference. So the choice is yours, but normally I will tell you, like, the activation function you choose would be mostly a leaky ReLU or something like this, which have been found quite distinct. But this activation function, choice of activation function does not affect the accuracy most of the times, because some activation function will lead to convergence much slower. So that's the reason why we don't emphasize much on why you use this, why not this. So using some good activation function for your problem may accelerate this thing, because as we saw, the ReLU leads to dead neurons, and other things have some more computation is involved. So there are different challenges you face. Okay. So this is sigmoid and tan h past, and some people use sin x also. So it's also a nonlinear function. You can use it. So these are some choices. So this is the summary of all the activation functions: ReLU, leaky ReLU, shifted ReLU. This is max out. You build a nonlinear activation from several linear activation functions. Soft plus, this is ELU, exponential linear unit, which is the smooth shifted value, and this is sigmoid, tan h, and swish. Yeah. What is the hyperparameter here? Oh, okay. So to choose which activation function is good. That's what I told. Normally we choose leaky value and don't bother about that. Choice of activation function has never been done using hyperparameter, because if you choose the right activation function yourself, no one questions. Everything will, the accuracy has very less effect. So let's come to the final layer. One more building block we need to understand, which is called softmax. Okay. So suppose you have a 3-class classification problem. Normally you do a encoding called one-hot encoding. What is that one-hot encoding? Anyone? Yeah. So you have a vector. Finally, you have during the training phase, you will encode it as 3-class, means the output layer will have 3 neurons, and while training, you are going to give 1 to the correct labeled class and 0 to others for every training example. Okay. But during inference, the problem would be, or even during training, when you calculate the error, the problem would be to achieve closer to it. So whatever comes out from the last layer, you need to, the best possible scenario is your neural network functions very well and gives a one-hot encoded thing. Then 0 error you can reach for all the examples, training examples or test examples. But that is not possible. But that there would be some probability only it can say that deep neural network that this object, or let's say the image recognition task, this image has this category. So there may be some slight probability for other classes also. So we'll always get 0.94, 0.02, 0.02, or 0.9, 0.6, 0.06, and 0.04, something like that. So normally you expect the one-hot encoding itself, each of them is a PMF, probability mass function. Right? The probabilities are summing to 1, right? 1, 0, 0. So all other classes are going to be 0. So you expect the last layer to output a PMF also, probability mass function. Then the probability mass function, the vector, you can go and check the index for which maximum probability is there. Right? And then output that as the predicted class. So how to achieve that? This softmax function helps us achieve that. So what you do is, whatever be the output of the last layer, right? Whatever be the output of the last layer, what we are going to do is, we are going to raise it to the power of e, and then divide by the sum of exponential of all the other scores. If you do that, what will happen is, you will get probability of A, probability of B, probability of C. It is a probability mass function. So for a 3-class problem, the random variable is the one which is going to take the particular class of that object. Could be 1, 2, or 3, or here in the case A, B, or C. The random variable can take A or B or C. So let's say in random variable it cannot take A, B, or C, so it is 1, 2, 3 class. So what is the probability of class 1? What is the probability of class 2? What is the probability of class 3? That is provided by this softmax function through this equation. So every classifier in the deep learning uses this softmax function as the last layer, because of some other nice properties where you can back propagate easily and everything. So here is an example. So what it does is, so there is some ambiguity, it clears it very well. So the output layer outputs some range of values. It need not be from 0 to 1 also, and need not sum to 1 also. And after you pass through the softmax layer, what happens? So the first one clearly tells that C has higher probability than all others. And the next, for the next example, the Softmax layer says that D has higher probability than all others. And for the last example, also it's a 8 class classification problem. D has higher probability. Right? Everyone understood this? Okay. No, activation layer is different. So this is the last layer. Always the output layer will be the softmax layer for the classifier. Yeah, every time, because it is differentiable and all the back propagation, everything. Because it converts any set of outputs coming from the layer prior to the output layer to a probability mass function, or probabilities corresponding to different class labels. So it is easy, right? So always you are going to get a set of values as output from softmax layer, which are going to sum to 1. It's a valid probability mass function. So you output that class as the correct class, which has the maximum probability out of those which are output by the softmax layer, which is the last layer. Everyone understood this? Okay. So this completes our understanding of the architecture of MLP. Okay. So the multi-layer perceptron, if you want to use as a classifier, what you will do, you will stack a lot of layers. Every layer does weight matrix times the input vector for every neuron, followed by a nonlinearity, which is the activation function, the choice we have seen. And finally, you will have a softmax layer. Okay. So now let's understand the difficulties of this MLP. Why we have to go to this convolutional neural networks? Anyone? What are the difficulties? Huge number of weights. Yeah, huge number of weights. So you need to do a lot of back propagation. So you need to change so many weights. So it affects the storage, right? You have to store so many of the weights, and also you need to do more computation, because a 1 megapixel image, the input layer will have how many weights? 10 power 6, right? 10 power 6 is the input size. So each neuron, you are going to fully connect it, right? 10 power 6 weights for each neuron in this thing, input layer, and it would be tremendously complicated to for you to learn it in a finite time. So then people came up with this notion of convolutional neural networks, where the primary idea is weight sharing. Okay. So instead of learning a weight for every particular thing, so can we have some concept of weight sharing? Okay. So instead of the fully connected layers, which are part of this MLP, these convolutional neural networks have the initial layers at least as convolutional layers. They are convolution operation, which we discussed in the. So we'll see the architecture of CNN one by one, but just I want to summarize it. So they are called CNNs or ConNets, convolution networks, and so on. So because of the weight sharing we are going to introduce now, it's going to do faster computation, and the weights are going to occupy lesser memory. And we are going to use the neighborhood info, which is called a receptive field also, to achieve that, and less number of connections also, because the weights are less, we will have sparse connections also. So these are the advantages of convolution networks than the multi-layer perceptrons. So what is the difference between multi-layer perceptron at the architecture level and convolution neural networks? Multi-layer perceptron, all the layers are fully connected layers. Convolutional neural networks have both. So it's not to all layers are convolution layers. It has the initial layers as convolution layers, followed by some fully connected layers. Some of the architectures we see. Okay, so we want to take advantage of these convolution layers till we reduce the dimension of the input to an acceptable range. Then if we have a lot of fully connected layers, that is tangible, we can do well. But at the beginning itself, you start putting fully connected layers, then it explodes and it's having a lot of problems. Okay, so let's understand this. Now we are going to have some, let's introduce some notion before proceeding further. So image, if it is a grayscale image, it's a 2D thing, right? But if it's a color image, it has 3 channels, red, blue, green, right? Let's use the same terminology of channels to specify how many of those 2D are stacked. It's actually a tensor, 3D tensor. Color image is a 3D tensor, and grayscale image is a 2D matrix, right? So the tensor, we want to specify a name. So this M cross N is the spatial, spatial dimension, and 3 is the number of channels. Here the number of channels is 3, R, G, and B. Red channel, green channel, and blue channel. So some other representation can have this also, this kind of thing. Here, this is the spatial dimension, and there are, I think, around 8 channels here. The 8 channels are taken out from 1 pixel location. So every spatial location, you can pick out that dimension. Okay. So let's use a toy example given in the textbook itself, the Glassner's book I'm referring to. Now, what we want to do is, given an image, we want to detect all the pixels which are yellowish. So let's, it has 10^6 pixels, but let's do it for 1 pixel. Then the same algorithm we can put for every pixel. So what the algorithm we are going to do using this thing is, using neural network, is you take the, go to one particular location. So one particular location and pick out this green, blue, and R channel intensity values. So all of them will be within 0 to 256 for a normal image, right? Each value can, each of these can be from 0 to 256, right? So what we are doing now, we are giving +1 weight to the red value, +1 to the green value, and -1 to the blue value, sum it up and pass through a activation function. Okay, so now these guys, these weights we are doing, we can call them to be filters or kernels. For this problem, always we are going to detect this, whether the particular pixel is yellow or not, right? So the weights are not going to change for every pixel location. Everyone agree? So once we find the weights by some means, so here we are hard coding it as +1, +1, -1, be anything. Once we find the weights for one particular pixel in the image, the same weights we can use it everywhere in the image, right? So the benefit is what? Huge. That's all the neurons, you consider all the pixels as different neuron of the input layer, share the same weights, right? Now you understood with this toy example why they are beneficial. So if you look at this diagram, so we use these weights, this +1, +1, -1 as the weights, and then take out the pixel location, pass it through the activation function, and output whether it is yellowish or not. So you repeat this for every pixel. So traditionally, you can write this as like this: take out this pixel, pass it through this neuron we define, right? And which can comprise of this this entire thing. This we call it a neuron, right? So you pass it through it, and the output you get. The activation function, whatever comes as output, using which you can predict whether it is yellowish. So you do this thing here for a real image, +1, +1, -1. So from the color, this thing you can see yellow means it should contain more of blue and green, but less of more of red and green, and less of blue, right? So the color chart you can easily find out. So you do it, do +1, +1, -1, red +1, green +1, and blue -1 for every pixel in this image. You ended up detecting almost the yellowish thing, right? This is the key idea behind convolutional networks. Here, how many weights you had? Only 3 weights, right? Okay, everyone understood this? It's able to identify the yellow pixels because frog was yellow. We are getting there. It's not able to identify the frog yet. It's a toy example just. So if there is some other object here yellowish, so it will detect that also. Okay. Now let's go further. So what we internally did was the shared weights were stored here somewhere, right? What we did was take out this and take inner product with the shared weights, pass it through an activation and got the output. This is what happened here. It's a toy example. We have not yet gone into CNN, but just to make you understand the power of weight sharing. Okay. So for an example, another example I told in the last class also, again, I am going to say, like, this is what previously in image processing people were using. Here we are hard coding the weights, but we are going to learn the weights in deep learning or neural networks. That's what we are going to say, right? Here, what I wrote a filter 1, 2, 1 and -1, -2, -1. Here it is another filter, Revit filter, I think. So this image you pass it through this filter, and not this image, the cleaner image. So it will detect all the horizontal edge, and this will detect all the vertical profiles. So that is working. This is also kind of weight sharing only. The filter kernel was only 3 cross 3, but the same filter you shared across all the pixels and you are able to do it. Similarly, this one is an averaging filter. It is going to blur the image. So this is a low pass filter, which is going to filter out. So here also the weight or filter or kernel are shared across all the pixels in the image. But the fundamental difference is that +1, +1, -1, the weights for this yellow detection, and for blurring the image or detecting horizontal edges and detecting these vertical edges, we use some hard-coded weights. But in actuality, we have to learn these weights. Okay, the filters or kernels are learned during the training phase. Any questions still here? Everyone understood the transition between MLP and the CNN? So this is the process we saw earlier also. This this thing is a convolution followed by nonlinearity. So what we are going to do is, if we have only one layer image of this is the image, and this is the weights. Okay, so what we are going to do is this weight. So this is an inner product explained in a very detailed manner. So inner product has 9 multiplications for a 3 cross 3 image with a 3 cross 3 neighborhood of the image with a 3 cross 3 filter. So what happens is there is a multiplication between this and this happening, and this pixel and this is happening, and this pixel and this weight is happening, and so on. So 9 multiplications happening, and all of them are summed up and passed through a nonlinear. This is one inner product. So one inner product will give me one output. So I have to repeatedly do. Then I have to shift it, do an inner product, then get another output. Shift it, do another inner product, I'll get. So this is one inner product. This is a single inner product. So single inner product is single step of a convolution process. It's not the entire convolution, right? Single inner product will give one output. So you need to construct the entire vector of the output. You need to do it repeatedly by shifting it at different locations of the input image. But the fundamental idea is this weight is not going to change from one location of the image to another. Okay. So this is another way to represent it. So you keep it at this central pixel, this weight, and then take a inner product, you get one entry in the output. You want to get another entry, what you will do? You will shift it somewhere this side, and get all the. Right? After you had placed this weight on all the possible locations in the input image or input matrix, you would have done convolution. And you would have got all the entries in your output. Everyone understood this. So the main advantage is this one is shared across wherever I am going to keep. So this is an example of placing it in multiple locations. You place it at this location, you get this output. So here we are not padding anything. So, and here you keep, this is the output, 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 here you keep. So keeping this weight or the kernel or the filter at different regions, you are able to get the different outputs. Any questions? Everyone understood this? Okay. So let's do a toy example to understand this. Suppose this is your filter. And this is your input, right? This is your convolution output. So what we are doing in this toy example is it's a 3x3 filter. So this 1, 1, 1, all others are 0, 0, 0. This is the filter or the kernel. This we are placing it at all possible locations of the input, taking inner product and getting these values. Then we are using a non-linearity or activation function. This is the activation function. After activation function, you pass this string through an activation function. This you pass it through an activation function and get this output. So what has happened? What has happened here? So it has, this filter gave high response wherever the pattern in this original image matched this filter. The inner product will be maximum at those places when the filter kernel or the weight matrix matches the particular thing. So if you closely look at it, this region matches this filter. Yes or no? So that's why you got a strong response in the output. Similarly, this another region here, this region matched this filter. So you got a strong response here. Okay, this is just showing that same region I indicated. So next, let's do one more example. So let's have this as the filter kernel. This is a shared filter kernel or the weight. And this is the input. This is the convolution output. And we pass it through a nonlinearity or activation. This is the activation output. And this is the region you identify. So you can see that this has 1 and this is 0. So this thing, you can find a similar thing somewhere here. I think somewhere here. Okay, somewhere here. So you get a strong output here. Similarly, somewhere here also you get a similar thing. So internal mechanism, this is the one which is happening at every layer or every neuron of your convolution neural network. Any questions here? So the weights are shared at every location, and you are getting the highest response at places of the input where this thing matches the filter kernel. Yeah, it is like, that's what I told, convolution is analogous to correlation. So correlation will be maximum when both of them are looking same. So So effectively, we are doing the convolution name in a convolutional neural network is misnomer because we never flip it this way and this way. So we just place the kernel or the filter or the weight matrix at different locations. So why it is shared? Because the same filter is used at different locations. So this is about the padding. I don't want to emphasize much, but if you want the output after a convolution process to be of the same size as the input, you need to do something called padding. Otherwise, this is the filter receptive field. If you want to place it on the matrix and get an output. So suppose this one you are keeping it only when it is fully within the input. So you will lose some dimensions, 2 dimensions here, and 2 dimensions here, and 2 dimensions here, and 2 dimensions here. So what you need to do is you need to pad some zeros so that it doesn't go out of it. So you normally pad to whatever amount you are losing, and then you keep all the filter area, then the output will be of the same size of the input. So you can do multiple types of padding. You can just pad zeros, or you can do reflection padding. So this you can reflect on this side, and these you can reflect, and this you can reflect. So there are multiple ways you can do the padding. Or you can repeat this value, you can repeat throughout, this value you can repeat throughout. So the convolution kernel then will be able to span all the locations of your input so that the output dimension same as the input. So normally it is specified with zero padding or without zero padding. If it is without zero padding, always the output dimension will be less than the input dimension depending on the size of the kernel. The size of the kernel is large, then the dimension of the output will be much smaller than the input dimension without zero padding. With zero padding, always the output spatial dimension I am talking about will be same as the input dimension. So this is an example. So you pad it, then you get the same thing. So let's extend this the weights to a, let's say we saw two dimensional weights. So how to define the weights if your input data is 3-dimensional? It's a tensor, right? So if it is a tensor, so if you have a input which is a stack of 3 things, so then the weight also should be like spanning the number of channels also. So an example you can see here, this is the input and this is the weight thing. So what you need to do is this, actually the one cube is there, another cube is there. So this cube will like enter into it. It's an inner product happening in the tensor space, right? So or you can realize it as multiple inner products or 3 inner products happening in the 2D tensor space or matrix space, and then they are summed up. Like this channel taking inner product with the first channel of this, and this middle channel taking an inner product with the middle channel of this, and the third channel taking an inner product, then followed by the ReLU or any activation function. Okay. So now let's have another variation of this scheme, which you will see in several CNNs. So now you have only a 2D thing as the input, 2D data, or a matrix as the input, which is a 3x3 one. But you want to have like more values as output. For an example, if you want to like if you take only one 3x3 filter and take an inner product with this, only one output value you will get. But you want 4 output values. So this is useful, like for the classification problem, we saw that the output layer outputs 4 values. Right? For such cases, you need to increase the number of values. So in that case, we can have 4 3x3 filters. Here, what happens is the input is the same for each of them, right? But the output, the weight matrix is comprised of 4 into 3 into 3, that many weights. Okay. The first channel of this weight matrix, also the filter, will take an inner product with the input, that is passed through a nonlinearity, and you get an output. And then the second channel of the filter, because the filter itself now is a tensor like this, right? So this is 4. So the first one slice you take and take in inner product with the input, and take the same input, take with this inner product with the second slice, and so on. Then you will get 4 output values. This is another variation. So we'll see some classical networks. So then you will be able to figure out which is what. Okay. So the basic idea I want to point out is the image processing or the computation in the traditional sense. We're also doing the same thing, but the weights were fixed. We saw some examples: Sobel, Pravit, average filter, okay, which were doing edge detection and blurring and so on. And some of other examples I've written: Gaussian, Laplacian of Gaussian, bilinear, and so many other kernels. So the task was already predefined. You gave the weights already and then used it to do the task. But in the deep learning, we are going to see in the next session, I will take some more time. So it's a representation learning in the sense that the filter is learned. So what goes in the filter is not a priori known. Like Laplacian means it should have 1, -4, 1, 1. So it's like -4 at the center, 4, 1 at the east, west, north, south direction, and 0s in there. So something like that. It's a second derivative filter. So, but we don't know like what is good for me. So given a data, I don't know what filter will work, what will not work for me. So I leave it to the network itself to decide on the best choice of the filter to get the least possible error in the error function or the cost function. Okay. And the deep learning filters are also high dimensional filters. So one of the high dimensional filter I just introduced. So it's a high dimensional tensors or the filters or the tensors. And there are going to be hierarchy of filters. So the image processing, you do one thing and leave it. So here we are going to have one layer will have one shared set of filters, and then next layer will have another shared set of filters, right? And all of them are learned simultaneously. And if you compare in the same sense with the traditional machine learning, there was a feature extractor earlier. But here these learned filters in deep learning network or the convolutional neural network, which we are specifically discussing, these learned filters act as the feature extractors. The first few layers we are going to see in the next session, that first few layers are going to act as feature extractors for the following layers. Learned filters means the weights or that thing I wrote down, right? Here we had some examples we took, right? I think here. So for an example, given an image you want to blur, this is an average filter. These are the entries of this filter, which is already known. So these entries are not going to be hard-coded or engineered a priori in a learned filter. Yeah, no, already known. That's why it's called the engineered filter. You can say it's engineered filter. Learned filter, we are going to learn it. We are going to learn during the training phase of the supervised learning. So the initialization scheme I talk about Gleraut-Hay and other initialization scheme for the weights. So similar scheme we will use for convolutional neural networks. Either you use sample from the uniform random variables or Gaussian random variables and initialize those weights and leave it at that. Then what should be the ideal entries in the weights will be decided by the network as it completes the training phase. Okay, that's why we are having a relation between the traditional computation image processing things, which they're using like hard-coded filters like these things. So this is called a Pravit filter. The name of this, which detects only horizontal edge. This detects vertical edge. But we are going to see through visualization in the next session that these things automatically evolve also. But we cannot say that this filter in a convolutional network is going to detect only horizontal edge. But after visualization, you have to backtrack and say that, oh, this filter was learned to do this task. That inference you can make. But a priori, we are not saying this filter is have to do this task for me. Okay, any other questions? That we'll see. That I will do the analysis for some of the classical networks and then how to fix the dimension. So what is the, so how you have to choose. So we'll do that analysis, that tensor product and how we're going to do. So a couple of networks I will take. We'll analyze mostly VGG16 in the session, this thing, and understand it end to end in a sense. Okay. So as I told, convolution networks, we are going to see in VGG also that initial layers are convolution layers, and last few are going to be fully connected layers, and the last layer is going to be a softmax, because we have to classify the images. Any other questions? If not, we can conclude this session. So we'll meet again at 2 and have the last session. So I will talk more about the CNNs and then introduce you